So when we are diluting acids and bases, we are adding water to them, and in doing so, we are bringing their pH closer to 7 because we're neutralizing them by adding water, okay? So that means for acids, we are going to raise their pH as we add water, and for bases, we're going to lower their pH because we're adding more water, which brings them closer to neutral. So one thing to recognize, and you may have noticed this if you worked through some of those pH calculations, is that you should notice that every time the concentration changes by a factor of 10, so either the times 10 to the power of changes by 1, or we move that decimal place over by 1, we find that the pH changes by 1 single unit. So do recognize that if the pH changes by 1, that means the concentration changed by a factor of 10. If the pH changed by 2, that means the concentration changed by 2 factors of 10 or by 100. Sorry, my kids are playing with some loud beeping toy. Okay, so being able to go the other way. We've talked about how to calculate pH from hydronium concentration and pOH from hydroxide concentration, but you also have to be able to calculate the other way. So to calculate the concentration of hydronium, we are going to do 10 to the negative pH. So if you look at your calculator and you find that log button that you've been using, you should notice that the second function of that button on pretty much any calculator is usually 10 to the x, okay? So when you are typing these in your calculator, you're going to do that second function log to get 10 to the x, and then you're going to type negative and then pH into there. When you want to calculate concentration of hydroxide, it's just 10 to the negative pOH. So those kind of finalize those equations that if we were regularly in class, we would be asking you to have memorized, right? They would be the pH is negative log of hydronium, pOH is negative log of hydroxide, that pH plus pOH equals 14, and then these two equations here, which are hydronium is 10 to the negative pH, and hydroxide is 10 to the negative pOH. Okay, you're going to find in Chem 30, if you are taking that, we will use those equations pretty extensively when we are in the acid-base equilibrium unit. So you do want to make sure that you know how to calculate and that you kind of have a good understanding of how to use these equations. Okay, so looking at just a really straightforward example, so calculate the hydronium ion concentration of a solution with a pH of 2.47. Okay, so in this case, your one given is that the pH is equal to that 2.47. So our equation is that the concentration of that hydronium is equal to 10 to the negative pH, okay? So we're going to have that this is equal to 10 to the negative 2.47. So you go to your calculator, you do that second function of the log. It should be showing you 10. Some of it will show like a little 10 hat, so you will just say 10. And then you should be able to just type in negative 2.47, and you should be able to get an answer out of that, which is going to be, I'm still in superscript mode, hold on a sec, 3 point, how many sig digs do we have here? Okay, so going back to those sig digs before I write down this answer, remember pH numbers are weird. So this is 2.47. So there's the 4 and the 7 after the decimal, which means this has 2 significant digits. When I get my concentration, this has normal sig dig rules. So the 3 counts as significant. So it's going to be 3.4 times 10 to the negative 3. Okay, and this does have units, and I have to make sure that I don't forget about those. Okay, so it's going to be moles per liter because it's a concentration. So sig digs go backwards, right? Look at decimal places to be able to determine total significant digits. Okay, so our next example is calculate the barium hydroxide concentration if the pOH of the solution is 2.50. So we want to take a second and think about it. So if we know the pOH, what we can get from pOH is concentration of hydroxide. The question is asking us to find the concentration of barium hydroxide. So because we're dealing with an ion concentration, we're going to have to write our dissociation equation. Okay, so we're going to have our barium hydroxide, and then this is going to dissociate into those barium ions. as well as 2 of our hydroxides. Oh, sorry, my computer's really rocking. Let me fix that up a bit. Okay, so what we know right now is the pOH. So that pOH is associated with that hydroxide ion. We know that the pOH is 2.50. So what we can calculate from the pOH is what the concentration of that hydroxide ion is. Okay, so concentration of hydroxide, if we think about the equation that we've learned about, is 10 to the negative pOH. Okay, and we know what the pOH is. So we're going to do 10, I don't know why it's all the way over there. What did I do? Okay, it's going to equal 10 to the negative 2.50. So we can go ahead and calculate what that is. So 10 to the negative 2.5. So we get that the concentration of hydroxide is equal to 3.16, and that number does keep going, times 10, oh, hold on, I've gone and left myself in superscript mode, times 10 to the negative 3, and this is going to be moles per liter. Okay, this is a bigger number than that. If you want to put that ... just to represent that it is a bigger number, you definitely can do that. Now that we know the concentration of hydroxide, now we can do our unit analysis to get our concentration of barium hydroxide. So we can set that up. So concentration of BaOH2 is going to equal, so it's going to be our ratio. So in this case, because we are trying to find barium hydroxide, we're going to put that on top. So 1 mole of BaOH2, and that is going to be over 2 moles of that hydroxide. Okay, to get rid of moles of hydroxide, we have moles of hydroxide right here in our concentration. So we are then going to times by that 3.16, making sure we're using that whole number, times 10 to the negative 3. And that's going to be moles of OH minus over those liters. Okay, again, take a look at our units. We're going to see that we can cancel out moles of hydroxide, and that's going to leave us with moles of barium hydroxide per liter. So we take our answer, because we want to use that whole number, and we divide by 2, and from there we can get our concentration of barium hydroxide as 1 point, well, how many significant digits? 2, because our pOH had 2 numbers after the decimal. So 1.6 times 10 to the negative 3. Again, because this is a concentration, we need to make sure that we pop those units of moles per liter into it, okay? So we converted pOH to get concentration of hydroxide. Once we have the concentration of hydroxide, we are able to do our unit analysis to calculate that concentration of barium hydroxide using our ratio. Okay, last example. So calculate the mass of sodium hydroxide required to prepare a 500 ml solution with a pH of 12.75. So we are trying to get the mass of NaOH. So when we look at what we're given a pH. So if we think about it, pH usually is associated with an acid. Right now we have a base because sodium hydroxide is a base. So first thing we want to do is we want to convert that pH over to a pOH. And we're going to do that by doing 14 minus that pH. Okay, so we're going to do 14 minus 12.75, and we are going to get 1.25 as that pH, or pOH, sorry. So what we can do with pOH, like we did in the last question, is we can calculate that concentration of hydroxide. So again, we can set up our dissociation equation, right? So NaOH, I'm going to start it as a solid because we're looking for a mass of it. And this is going into water. And then this is going to give us a sodium ion as well as a hydroxide ion. Okay, so we now know the pOH is 1.25. So from that, we can calculate the concentration of the hydroxide by doing that 10 to the negative pOH. So we can do 10 to the negative 1.25, not 3, 5. Okay, so from here, I can calculate that the concentration of that hydroxide is 0.0562, and that keeps going, okay? And that's moles per liter. All right, so we are looking for the mass of NaOH, right? We are trying to find this. This is our unknown. So we're going to need to get a molar mass, right? Anytime we want a mass, we need a molar mass. So we get that, and it is 40 grams per mole. Ew, that was not what I meant to hit. Underline. Sorry, I should probably put that 0.00, right, so that I don't get confused on my significant digits. What else do we know? We know the volume, right? We were told 0.500 liters. And so now we can go ahead and do that unit analysis. So now we're trying to solve for mass. So we think about what unit mass has. Mass has units of grams. So I look at all the different givens that I have. This has grams. It's associated with NaOH. So this is what I'm going to start with. So I'm going to start with that 40 grams. And that's going to be per mole of NaOH. Okay, I need to get rid of moles of NaOH. The only other place I have moles is over here with hydroxide. So to convert moles of NaOH into moles of hydroxide, we're going to use a ratio. So we're going to do times. What's going to go on the top of the ratio? Well, I need to get rid of moles of NaOH. So I have 1 in my equation. So it's going to be 1 mole of NaOH. And that's going to go over 1 mole of OH minus. Right? Because that is what I have information for. So from here, I can cancel out the unit moles of NaOH. The next unit for me to cancel out is moles of OH. So again, I look at my givens. Well, this has moles of OH, so I'm going to use this. So I'm going to say times 0.0562, again, making sure I'm using that whole number in my calculator, moles of NaOH, and that is going to be per liter. Just extend that page. And so now we have canceled out, oh wait, why did I write moles of NaOH? So that's not moles of NaOH. That is moles of that OH. Okay, now we can cancel out moles of OH. So now we have grams per liter. We don't want liters, right? We just want the grams. So we need to get rid of the liters. We're going to get rid of the liters using the volume that we have over here. So we're just going to do times. That's 0.500 liters. And we're just going to put that over 1. Okay, so again, go back, look at those units. We now get rid of liters. We look at all our units. We only have grams left because this canceled, and this canceled, right? So basically we kept canceling until we got to the end, and all the units were gone except for the one we wanted. So we are going to do this in our calculator. I just have to re-enter that times 10 to the negative 1.25 because I want to make sure that I'm using that entire 0.05623 number. So now we can do our 40 times that number, and then times 0.5, and we get 1.35, wait, nope, too many significant digits, 1.3 grams, okay? 2 sig digs because our pH that we were given in the question had 2 numbers after the decimal place. So 2 numbers after the decimal place corresponds to 2 significant digits. So I get to have 2 significant digits here. My calculator is reading 1.34. And so because a 4 is less than a 5, that's why it stays as a 3. Okay, don't get confused by the fact that there's a 9 after the 4 because we always just look at the next digit. We don't look previous digits and then start like rounding all the way back, okay? So 1.3 grams is what we come up with. So this is probably about as hard as these questions are going to get because we had to do the most work, right? We had to convert a pH into a POH, then we had to calculate a hydroxide, and then we had to do our big long unit analysis calculation, kind of using everything that we have so far, okay? So this is how you are going to calculate a concentration or a mass when you are given a pH or a POH.